Welcome to week 9 of Stat 428. This week's lecture is going to be short. However, we're going to introduce an important topic, which is permutation test. Let's consider a motivating example. To evaluate the effectiveness of a medical treatment, we collect random samples, XA and XB, for comparable individuals who received the treatment, denoted group A, and the placebo, denoted group B, respectively. We may perform the hypothesis test where the null hypothesis is that the mean of the outcomes in group A and group B are equal. The alternative might be two-sided, where they are unequal. If you want to do one-sided, that's an option 2. And to do this, to conduct the hypothesis test, we can construct a test statistic T. So here I gave the test statistic for the two-sample independent t-test, where t is given by the sample means difference between the two groups divided by the pooled standard deviation times the square root of this thing, which depends on the sample size in the two groups. So you might have learned this in your first statistics course. So if xi's in both groups are the samples from the normal distribution with similar variances, then we know that we may perform a two-sample independent t-test where the degrees of freedom is given by the sum of the sample sizes in the two groups minus 2. And in this case, one can compute the p-value. In other words, the probability of getting a t, the test statistic, as extreme or more extreme than the observed value t under the null hypothesis. And if this p-value is lower than some preset nominal type 1 error level, alpha, say 0.05, then we reject the null hypothesis and conclude that there's sufficient evidence that the mean of the outcomes in the two groups is not equal. So this is the two-sample t-test you are familiar with, which is a parametric hypothesis test. Our question is as follows. In practice, one may not want to make such distributional assumptions about X. We might not know whether X's are IID random samples from the normal distribution with similar variances in the two groups. The observed samples might not satisfy these distributional assumptions, or the sample size is relatively small and it is not appropriate for us to use asymptotic approximations. In these cases, we might not want to make such distributional assumptions because we know they can lead to negative consequences if the assumptions are violated. If you recall from a few weeks back when we discussed Monte Carlo inference, we showed that when the normality assumption is violated for the x's, the type 1 error rate for t-tests may be inflated. One question we might ask is, can we still perform a hypothesis test for difference between group A and group B without the distributional assumptions about X? And that leads us to the topic of this week, which is permutation test. Permutation test is a resampling method that is particularly useful for hypothesis testing without distributional assumptions about X. You might also hear it being called randomization test or exact test. Like the bootstrap and the jackknife, permutation test is also a resampling method where we do the hypothesis test by employing resampling from the observed samples we have. However, different from bootstrap and jackknife, which are often used for approximating the sampling distribution or the byproducts such as the standard error or bias of a statistic, permutation test is particularly useful for doing hypothesis test. Also, unlike bootstrap, which relies on sampling with replacement. Permutation test involves sampling without replacement from the observed sample. So the permutation tests in general are often applied as a nonparametric test for the general hypothesis as follows. H0 is that some distribution f is equal to distribution g, and the alternative is that they aren't equal. In this case, neither f and g are specified, so we don't know either of these distributions, and we don't want to make distributional assumptions. For example, we can test the difference between two samples. So where the null hypothesis is that the distribution of the data in group A is the same as that in group B. In this case, we do not specify what exactly is FA and FB. We can also test for the independence between two random variables. Here, our null hypothesis can be the joint distribution of x and y is equal to the product of their marginals. And the alternative is that that is not true. In this case, we are testing this null hypothesis, but we are not assuming fxy or fxfy follow specific forms. Later on, we will see examples and procedures for doing the hypothesis test.